Welcome to another video in the Sunrise series showcasing the outcomes of Use Case 1.2 Connected Perception Testing. Sub-Use Case 1.2-B, Red Traffic Light Violation by a Pedestrian. In this video, we test an automated driving system, ADS, at a signalized urban intersection equipped with V2X communication. We assess how cooperative V2X communication with surrounding infrastructure can improve safety and enhance awareness on highways. The goal is to evaluate the system's ability to respond to pedestrian red light violations safely. 3 parts of the SAF will be demonstrated, namely execute, test, evaluate, and some steps of the safety case building. The test case setup is based on simulations carried out in IPG CarMaker. The system under test is a cooperative advanced ACC that includes augmented perception, integrating information about the current and future states of traffic lights transmitted via V2X communications. The scenario is an urban intersection. The ADS system approaches intersection planning by utilizing infrastructure information about the current and future traffic light phases. Suddenly, it receives a message that a pedestrian is violating the red light. The scenario parameters are 4. The vehicle's velocity, the vehicle's distance from the intersection, the pedestrian's distance from the lane, and the pedestrian's velocity. The goal is to evaluate the conditions under which the system can avoid collisions and possibly use this information to better plan the approach. We followed a safety argumentation checklist that covered a microscopic evaluation of pass/fail results for individual scenarios, a macroscopic evaluation by aggregating the results into a surrogate model, and the use of that model to create safe approach speed recommendations. Key artifacts include coverage of the scenario space with a surrogate model that provides confidence levels, identification of high-risk scenarios and their boundaries, and determination of a safe approach speed. We will show these steps. Execute. 1981 concrete scenarios with a TTI difference smaller than 4 seconds were selected from 50,000 random points and simulated in CarMaker. Test, evaluate. A surrogate stochastic predictive neural model was trained and used to resample the logical scenario near the collision boundary. Execute. 572 new concrete scenarios were simulated. Safety analysis. The final surrogate model was trained on the 1981 plus 572 balanced dataset. Provides fast prediction with confidence levels. Safety analysis. The surrogate model is used to find unsafe conditions for 2 risks: walking and running pedestrians. Safety analysis. The surrogate model is inverted to synthesize a safe speed recommendation function. These are the 1981 concrete scenarios with a TTI difference of less than 4 seconds, selected from 50,000 random points and simulated in CarMaker. The red dots are collisions. They may happen if the pedestrian crosses the lane less than 5 seconds before the car's arrival. We trained a first surrogate stochastic predictive model and used it to resample the logical scenario near the collision boundary. 572 new concrete scenarios near the collision boundary were obtained and evaluated, providing a balanced set of collision/safe examples. The final surrogate model was trained on the 1981 plus 572 balanced dataset. The model is biased toward high recall of the collision class. The surrogate model provides collision predictions with confidence levels, the shades of red. It was used to find the unsafe regions for 2 risks: a pedestrian moving at walking speed, on top; a pedestrian moving at running speed, at the bottom. The unsafe domain was inverted to derive a safe approach speed recommendation, subject to 2 meters per square second maximum deceleration. The picture shows the safe speed, i.e., the speed that allows the ADS to stay out of the unsafe region, for pedestrians either running or walking. In this video, we have shown test results aggregated into a surrogate model, iterations to balance the example set, finding the unsafe region with confidence levels, inverting the safe region to derive a safe approach speed. Concerning limitations and future work, the following comments apply. Human intervention is required to adapt the method to different logical scenarios. Human intervention is necessary to interpret the results. Automating the process may be necessary for optimizing the surrogate model hyperparameters.